Question 2. This question is about the silicon related question. Part A. Silicon is extracted from the silicon dioxide by reaction with carbon over 2000 degrees C, which follows the reaction 1. Part 1. Explain why entropy change, the delta S, of the reaction 1 is positive. First, we need to refer to the state. See whether it's formed gas or is formed solid. Okay, so from this reaction 1, we know that is from the solid to form liquid and gas. Means is from less random to become more random, because liquid and gas is more random. So means after reaction, the whole mixture or the system will become more random or more disorder. So we know that the delta S is going to be more positive because of this. So what you need to write is just 3 moles of solids here, 1 plus 2 moles of solid. So 3 moles of solid form 1 mole of liquid and 2 moles of gas. That's why delta S is positive. Part 2. Reaction 1 is highly endothermic. So suggests the effects of an increase in temperature on the feasibility of this reaction. When you want to answer this question, so better use the Gibbs equation. So delta G equal to delta H minus T delta S. From part 1, we know that the delta S is positive, and in this part 2 already told you delta H is positive, is endothermic. Now, if let's say both positive, we know that delta G, because it depends on these two enthalpy value. If is a delta H, means it's endothermic reaction, delta G is actually something like is more likely to be positive, but still need to depends on the entropy values, because now entropy is positive. So means negative T delta S can be negative enough to overcome this endothermic value. Means this delta H, which is positive. So how to make this negative T delta S or the T delta S larger? So by using the temperature. If the temperature now increases, so we know that T delta S, this one, is going to be larger. So the delta H now minus a larger value, eventually delta G will become negative. So until the point that means the temperature when it's increased, until the point that T delta S is larger than the delta H, then the delta G is negative. So that's the point, right? So this is what you need to write. As the temperature increases, so we know that T delta S will become more positive, or you can say negative T delta S will become more negative. So therefore, delta G will become more negative as temperature increases, because somehow when temperature increase, this T delta S will be larger than delta H, eventually delta G will be negative. So therefore, the feasibility of the reaction will increase with temperature. And for those who not really clear about the feasibility of a reaction with delta G, remember, delta G when it's more negative, the reaction is more feasible. That's a concept. part B. So we have a reaction 2, the reactions between the silicon with the HCl from the SiHCl3 and H2. You can predict the delta S sign actually is from 3 moles of gas now from 2 moles of gas here. So we can actually predict the delta S sign is negative. So we can prove that by calculation now. Part 1. Entropy data is given for these 4 reactants and the products. So use this one to calculate the delta S. So to calculate delta S, we need to use the sum of the entropy of products minus the sum of entropies of reactant. So substitutes all the entropy data. So this one is a product. 314 is for the SiHCl3. 131 is for the hydrogen minus 19 is for the silicon plus 3 times because the coefficient here is 3 times of the 187, so which is the HCl. So therefore you will get negative 135 joule per Kelvin per mole. Okay, for this part. Okay, so remember it's negative 135 joule per Kelvin per mole. Part 2. Now we have a reaction 3. Now reaction 3 is the reverse of reaction 2. So this is a very important hint. It's a reverse of the reaction 2. And for this reaction, now the SiHCl3 with H2 form silicon and HCl. Enthalpy is given, which is positive 219.3 kilojoule per mole. Now, this question wants you to calculate the temperature in Kelvin at which the reaction 3 becomes feasible. So first you need to use the entropies that you obtain in part 1, because in order to calculate this temperature you need to make assumption like this: delta G equal to 0, therefore delta H minus T delta S is equal to 0. The delta H is given now here, but the delta S you need to find or get from the part 1. So the delta S for reaction 3 is negative okay, of the delta S of reaction 2 because it's a reverse reaction. So you just use this negative 135. So negative is positive. So the entropy for this reaction 3 is positive 135. So it's just a reverse of this the reaction 2, right? After that, substitutes the enthalpy and the entropy values here. Make sure you convert the entropy to kilojoule per mole, 135 over 1000. So it will from joule per Kelvin per mole now to this kilojoule per Kelvin per mole. Then you will get 1624.4 Kelvin. So this is temperature that is needed. Calculate temperature which reaction become feasible. Part C. Silicon can be produced by electrolysis of this silica, the SiO2, dissolved in the molten calcium chloride. Okay, this is equations that you should follow. Now calculate the time in seconds that required to produce 1 gram of silicon by this electrolysis, this one, using 6 ampere. So first thing that you need to do is to calculate the moles of the silicon. 1 gram over the molar mass of silicon, 28.1, So you get this mole. This is the mole of silicons that need to be obtained. If let's say we want to deposit, or we want to produce 1 gram of silicon, which is this mole, then from this equation we know that the reaction actually needs 4 moles of electron. Means in order to form 1 mole of silicon, it needs 4 moles of electron. Therefore, the numbers of moles of electrons that needed to form this mole is 4 times. So you use the moles of silicons times 4. That's the total electrons or total moles of electrons that needed, which is 0.1423. Then you need to calculate the total charge needed to produce this silicon. So total charge needed, because this one is the moles of electron, okay, is 0.1423 moles of electron. So this one need to times a Faraday constant. Faraday constant is the charge per mole of electrons. So this one is the moles of electrons that needed times the charge per mole of electron. So you get charge later. So you get this total charge that needed for the reaction, which is 13736.7 coulomb. So this one is a charge, means the Q. We know that Q equal to IT. I is the ampere, T is the time. So therefore, we need to rearrange. So because we need to get T, so it's a Q over I. So the Q over 6 ampere. Then you get 2289 seconds. If you want to double check, or you want to try to use another method, actually it's the same thing, no? This one, you can use Q equal to IT. Q is actually NZF. N is the moles of the silicons that produce. Z is the charge on the silicons. From here we know that is positive 4 positive, 4 positive. So because the Si with 2 oxygen, so this Z is 4, right? So basically it's Si 4 positive, right? Z is 4, and times the Faraday constant over the ampere. So Faraday constant over ampere, you get the same thing, similar things, 2290 seconds. Right, so this is the faster way to do it, but I recommend you all to use this method step by step, which is safer, right? Okay, that's all. Thank you.